So I'm really excited to welcome Anthony as we going to talk about building a virtual guitar pedal with PyAudio. And I'll let you introduce yourself, Anthony.
Sounds good. All right. So I'll use the mic. All right. So first, I was going to give a little bit of background on myself, and then I was going to just give a little bit of an overview about how digital sound works, just so that you have a little bit of context for what it is that I was doing on the project I've been working on. Then I was going to talk a little bit about like how reading and writing audio data works, again, just to get a little bit more background on what exactly it was I was doing. And then for the project that I'd been working on, I created kind of a crunch effect, a tremolo, a tuner, and like a square synthesizer type effect. So I was going to go through a little bit about how I did each of those and show the code for how I did it, and then I'll put the GitHub for where all the code is and the slides into the Discord. So if anyone wants to look through it in more detail, you're welcome to. And then at the end, I have a few other additional resources I found along the way that I could pass along to you all if you're interested in exploring further. So I'm a software developer for University of Michigan in the Space Physics Research Lab. I primarily work in the ground operations for satellites. The satellites we work on mostly do hurricane and soil moisture flooding tracking. I'm primarily a C++ developer, but I also do Python, MATLAB, and Rust. Um, yeah, so audio engineering is not my background. This was just kind of like a personal project. So for this talk, I'm going to primarily focus on the three tools on above that bar, the PyAudio, NumPy, SciPy, Aubio. So what those are doing is how I'm reading and writing audio streams. I'm using NumPy and SciPy to do various manipulations. And then I was using a library called Aubio to compute frequencies or, for musical, how it directly relates to pitch. Also, when you see the GUI, I'm using PyQt6 to create the graphic user interface. And then I have a few plots of sound waves in there, and I use matplotlib to create all of those. And then I used UV for the package management. Someone a few months ago here gave a great talk on how to use UV that I put a link to the YouTube talk on there. I've started really getting into it. It's got some really fast resolution, so I enjoyed getting to try out that manager for this project. Okay, so digital audio. So sound waves are waves of pressure moving through air. So what a microphone or another tool will do is capture these waves at various points. So you can see in that in this kind of graphic I have over here. Let me see if I can hide this. So what a microphone will be doing is at certain points on these waves, it'll be capturing the current state. And so what that allows us to do is in Python or another tool, we get an array of these points which correlate to some kind of wave. So usually the microphone is capturing, like a standard would be about 44,000 times a second or 44,000 hertz. And what that is that's kind of like an industry standard for how fast microphones sample because humans can hear around 22,000 hertz. So by sampling at twice that rate, it creates like a relatively lossless form, like a audio stream, so that when you play it back, you don't lose that much information. So the microphone or your whatever tool you're using to capture sound will create this digital array from this analog sound wave. And then that's where we'll do our Python manipulations. And then on the laptop or whatever system you're using, we'll use a digital to audio converter to take that array of points of the sound waves to vibrate your speakers or headphones or whatever to create the same sound waves that that you'd recorded. So for this project, the Python that I'm working on will fit after we capture the data via the microphone and before we write it back out to the digital audio converter to play through the speakers. So what we're going to be doing is doing different manipulations and reading that data to kind of create, to learn more about what the information that's being recorded is. Yeah, does anyone have any questions on any of that before I move on? Okay. Yeah, anyone feel free to stop me either in the room or online. If you have any questions or want any more details, I'm happy to answer anything. Um, so a couple things that I'm going to use throughout this talk are we're going to be talking about sample rate. So The microphone will capture these samples of the sound wave every so often. And so what will happen is we'll get a buffer of a certain amount of samples, then it'll call the Python, we'll run whatever Python code we want to it, and then we'll write that buffer back out after we've manipulated it. So for a standard buffer size, for example, that we're going to be using for this project is 2048. So we'll get 2048 of these little green points every time the Python is called, and then we'll manipulate it and write it back out. So you can see uh, this graph just shows a little bit of like what a higher sample rate looks like versus a lower sample rate. And so with the way that modern microphones work, what we're going to see is our data will look a lot more like this bottom row where there's heavy sampling throughout the wave. So that's kind of what the sample rate will look like. And then I mentioned this already, but buffer size is the amount of samples that you receive in the buffer sent to you and that will sent back out. So these are the samples on each wave, and the buffer size just refers to how many samples we get at each time. Yeah, does anyone have any questions on that? I'm not sure I did the best job explaining that, but yeah. So that goes through a series of magnetics through the pickup. I currently have my guitar wired into a Focusrite, which is a digital audio. I think it's a digital audio workstation, and it's going through USB into my laptop, and that is working at a similar. I can similarly manipulate the sample rate there, and it'll capture the guitar audio stream at certain points. So it'll still work kind of like a microphone, except instead of having a microphone, it's working off of the magnetics of the pickup on the guitar, and then feeding through with a USB to the laptop. But yeah, it works off the same way off of buffers and sample rates. Yeah, good question. Anyone else? Okay. Okay. So the other thing I was gonna mention just before we get too far into it is frequency and amplitude. So frequency is how frequent a wave recurs. So you can see on the top left, that would be an example of a relatively lower frequency where if the x-axis is 1 second, that would be 5 hertz or 5 waves per second. And the one on the top right would be 20 hertz or 20 waves per second. And so yeah, frequency will correspond to how fast the waves are coming in. And then amplitude refers to how big or how loud a sound is. And so when looked on a graph, a larger amplitude will look bigger and a smaller amplitude will look smaller. And that larger amplitude will correspond to a louder sound. And then the frequency directly relates to pitch. So frequency is more of like a signal processing term for how frequent waves come through, whereas it directly relates to a more musical term, which is pitch. So something like in the musical note A has a few different octaves it can be in, but it has a certain corresponding frequency that it runs at, which is what we'll use when we're looking at the tuner later on in the project. Okay. So the last thing I did before we dive into the effects was just kind of this caveat. So this is going to be working in a real-time environment. So there are some limitations to what I was able to do off of, just with these personal effects that I was making. So one of the limitations is that since it's a live environment, you don't know exactly what's coming next. So you can't perfectly smooth out different effects because you don't know what will be in the next buffer. It also needs to run fast because the more time you take processing that in the Python, there'll be more of a latency between when you record the sound and when it plays back. So if you're like playing an instrument and you hit a sound, it'll take a split second for it to come back, and even a split second can really throw you off if you're trying to play something and it sounds different timing wise than how you're messing with it. So yeah, again, these are just like kind of fun manual effects, mostly because it was a project that I wanted to work on to figure out a little bit more about how kind of the pedals that I'm using are working behind the scenes, but they're definitely not going to be professional level. But I do have some recommendations at the end from a library that Spotify put together that works nice for some higher quality effects. But I haven't seen anything that worked great at kind of a live stream experience they mostly work off of pre-recorded audio. But the Spotify, I think it's called Pedal Board, but I have a link to it at the end that it did do a pretty good job of like creating professional level effects in Python, but it's limited to only working off of audio files as of when I put these slides together. Okay, so the first effect that I'm going to go over is a crunch. So a crunch is kind of like it's a type of distortion. So essentially, what we're going to be doing here is it's similar to a process like if you were to play a song out of your, some kind of speaker, then you were to stick your phone up and record it and then play it back on your phone, it'd sound kind of like just, have that kind of like grittiness and kind of not, you'd lose some of the sound quality from doing that. So essentially we're going to do that in Python by, we'll have our input signal, we're going to make it a lot louder and then crop off the top and bottom of it and then normalize it so that it comes back to the same volume that it used to be. So this is what it'll look like. So on the left is the original recording of my bass playing in A1. And then on the right is what it looks like after the crunch is applied. So you can see after it was scaled and then cut off at the top and bottom, it kind of has that square shape on the end. So typically that'd be an undesirable effect because you're losing information, but it creates kind of an interesting distorted crunchy tone. So I am going to attempt to demonstrate this through the application I built. We'll see how this goes. Um, I don't know what saturation, I guess, means. Does saturation like making it more?
If you're sampling something
Mhm.
and you've run out of the So to saturate a sensor, you'd run out of the ability, like if a sensor has an ability to hear from 0 to 15,
Oh,
and that's what it measures based off of, or it only accepts a volume up to a certain level,
yeah,
then it's saturated because it's not able to fully record the true value. So it seems like saturation to me, where
yeah,
it's like the microphone could only pick up what are, I guess that's the amplitude, right? So it's like
yeah,
it's only able to pick up an amplitude up to 0.015 in this case, and then it's reached its limit and it
right.
can't interpret that it's louder than that, so it's saturated.
Yes, yeah, that is what we're doing. And then, so I do have on here, so you can change. I have some like tweaks that you can make, so you can change the threshold around, I guess, like where your saturation point would be, or where you cut it. And you can also change like the gain threshold. So I'm gonna start just by, okay, hopefully this will work. This is what the bass sounds like with no effect on it. And then once we add the crunch, which will yeah. So yeah, definitely has a clear sound to it, and you can change how much it cuts off. But it essentially is building a distortion by just playing it, making it super loud and cutting it off, like you were mentioning with the saturation. So in the Python code, let me pull this up for anyone curious. And again, I'll have this on GitHub.
Could those online hear the music? Thanks, Andy.
Yes.
So yeah, this one's probably the most simple of the functions. So what it is doing here is it's first just converting everything to a float just so that I can scale it, and then yeah, it's taking in a crunch gain, which is how much it'll multiply the amplitude by, or the signal by, to increase the amplitude. And I don't want to mess around too much going through all the different tweaks in here, but I made it so you can change the gain settings on here if you want to like increase it by more to make it more distorted or less distorted, and then also change where you cut it off. So this NumPy function called clip is what I'm using to cut it off at the tops and bottoms, and then um, that threshold is coming from the settings on the application. Um, oh yeah, go ahead.
Do you have a file of the data? Like, is the data sampling frequency sample?
yeah. So I am not taking a long-term recording of the data at the moment. I do keep a rotating buffer of the last few for a couple of the effects that we'll see later on. But yeah, right now it's mostly just this one is only purely working off. It'll look at the one buffer that it gets, apply this effect, and then move on. It doesn't actually record anything or right. So yeah, each point, yeah, each it's like each point on the what is it? Yeah, on the curve comes in. And so I'm applying the scale factor because that value will be either positive or negative. And so when you apply a scale factor to each value on it, it'll generally increase the amplitude of the waveform. So by applying a scale factor, which is the crunch gain, to each sample, it increases the amplitude. Does that answer your question? Okay. Yeah, anyone else have any questions? All right. All right. Let's get into it then. Okay. So the next one I'm going to talk about is a tremolo. So this is a wobbly kind of sounding effect. So what it'll do is it will kind of artificially drop the volume or amplitude of the waveform and then alternate between dropping it and increasing it or and going back to normal. Uh, Seems like more standard to only go from normal to lower. Otherwise, you'll kind of throw people off by just like making a sound that's way louder than they're expecting. And then I do a very small gradual increase and decrease on the effect. So that way, when it makes that jump between the loud and quiet parts, it doesn't create what's called clipping. I still have not perfected this, but clipping will be like a little ticking sound that corresponds to a waveform. Instead of having a clean kind of, more circular shape, it'll have a discontinuity where it jumps between things, and that'll create this artifact called clipping. So this is what the tremolo effect waveform looks like. So on the left is what the normal same thing the A1 played on the bass, and then on the right shows what it looks like when it artificially makes it smaller. It's a very short but gradual increase, and then up to normal. So I can demonstrate what this sounds like. So here it is with no effect. And then with the tremolo. You can kind of hear that, like, I don't know, kind of quiet, loud little toggling. So to the source code for how this is done. So this one I is a little bit more tricky. So the thing is that the buffer might not always line up. Let me see if I have a slide about this. Okay. So the trick here is that this, like the distortion, we could just apply a gain to it and cut it, and we only need to know what was in that buffer, and it was fine. This one, we need to know where we are in the effect because the buffer is typically shorter than we want the change between soft and loud. So we need to keep track of where we are in the effect. So for this one, I don't actually need to keep a full list of buffers going backwards. I just keep track of where I start each time where it gets quieter. And then from there, I can look at how long the buffer is and then determine when I should be in that buffer, when I should be going quieter and when I should be going louder. So in the code, that's what I'm doing here, just checking to see if I'm in a spot. I'm looping through just each effect or each sample in the buffer instead of doing something that applies to everything, just because it was a little bit easier to follow if I just loop through the buffer. And so what I'll do here is I'll keep track of my time since the last tremolo started. And then, if it's at below 0, I'll make it quieter. If we're in a part where it should be gradually scaling up or down is what I'll do in these two sections. And then finally, if it's, just a spot where it should be normal, we just pass back go straight from audio data to the effect data. And then I increment a counter. And then if we go over the time, since the frame length is how long each tremolo section should last, um, then resets the counter, and then we start the counting up for the effect again. Yeah, this one I still have at this particular depth and frame length. It seems to work well, but I can show you what clipping sounds like if people are interested in how I still have work to go on, I guess, perfecting how the tremolo works. But I guess before I do that, is anyone, it's not super jarring, but is anyone particularly sensitive to strange effects? Okay. Yeah, it's something to do with the, so it's mostly to do. I think it has more to do with the however long my gradual increase and decrease between the loud and quiet parts is. If I make it too quiet, then it's too short of a gradual increase that it makes a large jump, which causes that clip. So I'm changing the depth that started the clipping. And so what I think I need to do is I need to have my the length that I switch between loud and quiet be a function of how deep you go quiet. So like the more depth there is, the longer it should alternate. The longer it should take to go from quiet to loud.
So the depth is a ratio from normal to
Quiet, yeah.
diminutive.
Yes, yeah. The depth, yeah. It's like so we started at 0.5, so like the depth. So that would mean that the half, yep. So the quiet part is half. And so when I created that clipping, we went down to 0.3. So that means it was 30% as loud. And so it would probably need more time to adjust itself back up, is my thought. But I haven't explored that further. Yeah, that's good questions. Anyone else have any? All right. So next up is a tuner. Okay. So here I'm using a Python library called Aubio to use their pitch function. So this is, like you mentioned before, if we're keeping like a recording. So this one, I am keeping the previous 8 buffers worth. So what we're doing is keeping a rotating buffer of the rotating array of the last 8 buffers. So that'll give Aubio more data to work with, because it's going to try to compute a frequency off of the audio data that we're giving it. And by giving it more data, we give it a better chance at creating an accurate calculation. And that the sample rate of looking at, I think it was 2048 was my buffer size. About eight frame rates or 8 buffers seem to create enough of a stable tuning. So that function will give you the pitch function will give you the frequency. And then what I wanted to do was convert that frequency into essentially piano keys. So Wikipedia actually has a really good formula that was listed for it that works super well. So I cited them and I used their formula. So yeah, what we're going to be doing here is computing the frequency and then trying to determine which pitch it is, and then telling the user if they should go a little bit higher, a little bit lower. So that involves trying to find the pitch that you're closest to, and then figuring out how much you need to go sharp or flat. Or the sharp or flat meaning sharp meaning slightly more like higher frequency or higher pitch, and flat meaning slightly lower frequency. Okay, so this one is a bit more involved. Let me see here.
It's like auto-tune?
It's not auto-tune. So this isn't actually changing any effects. This is just reading the data and computing the note. So you can see, let's see on here. So right now I'm playing and it shows as an A1. I can turn off the tremolo so we know. So if I tune this down, you can see those, what is it, like carrots start to appear that tells me I need to go slightly up to reach an A1. So this is mostly meant to help get strings in tune. I can see that one needs to go down side a bit. And so if you're not familiar with musical termina, notes are have certain pitches associated with them. So these are like your A sharp, B, so on, so on. The number after it refers to which octave it's in. So I currently have a bass guitar that I'm using. And so it goes all the way down to what would be one of the lowest piano keys, which is E1, which is kind of testing the bounds for what Aubio can handle. So you can see it kind of twitching between E1 and E2. And so what we're doing is essentially we'll define what, and this is all based off a formula from Wikipedia, which worked flawlessly, is we define A4 as 440 hertz. And then from there, we can compute what all the different octaves and note names are. And so we'll give it a the frequency that we're operating at, and then we'll use this function to determine how close we are. So to any given note, and then I'll add more carets, whether, based on how much you need to go up or down to reach the exact pitch of that note. So this tap function finds what is the note you're closest to, and then then it calls this bottom one that makes the actual string that's being displayed, and it'll tell you how close you are to each note. And so I get each of those calculations as a floating point, and I have like the middle would be like 0, and then I go negative 0.5 to positive 0.5, and then kind of figure out where in between we are. So these ones would be a bit more to look at, but yeah, there's some great advice on these two sources that show a more complete definition of how this all works. But yeah, essentially all we're doing is trying to match the frequency to the note name and then tell you how close or far you are from any given note. Yeah. Any questions on the tuner? Yeah. Oh, that's a good question. I think it would just be very confused, but let's try it. Yeah, because I think it's because of how I'm hitting it. I wonder if I stroke. I'm picking up. Yeah, because I do every once in a while I'll see like that. So it's an A and E. Is it? I guess you're right. It's just picking up the bottom one. Yeah, interesting. Yeah, I never thought to try that. Yeah, any other questions from anyone?
Yeah, I guess that's interesting. That's kind of like in my head, I'm trying to think of what audio sampling is. And it's just, it must have multiple, I'm trying to think of if it just is an amplitude, I guess there's multiple waveforms on top of each other probably.
Right.
There's probably the bigger one that maybe shows up. I'm trying to, anyways.
Yeah, because so like an A1, so the A2 would have is at exactly double the hertz of A1. So the same note will kind of, I would pick it up between the two, but they'll kind of meet up at a certain, every other sample. Yeah, I don't know how exactly that would.
You don't have a picture output
For this one?
You just have the waveform output. You don't have like a monitor.
I don't have a live monitor. I do have a thing where I can create a plot, so I could try doing. Yeah, so that's how I make most of the graphics. Was just the.
That's probably like overlay wave interference.
Yeah.
One constructive and destructive interference of waves.
Yeah. So yeah, what I did try to have a live graphic going, and my computer started getting more latency trying to kick back the audio and do the live, so that's why I'd made just a button that plots like the last few seconds of data. But yeah, any other questions? Yeah, thanks for everyone for having good questions. All right, then the last thing I had, which is kind of like the culmination of all the other stuff I was working on, is called a square. So this is like a common sound on synthesizers. So what we're going to do is we're going to use the input frequency that we calculate and the amplitude that we calculate from the base, and then use SciPy to generate a square wave to make it essentially sound like a synthesizer. So yeah, what this looks is like, so the original base is on the left. Compute the amplitude from it. We get the frequency or the pitch, like exactly how we do in the tuner. And then SciPy will create that little square looking thing. So this sounds like here's the original, and then the square. That sounds like a retro video game kind of thing. Yeah, so how we do that in the code, let's see. Square. So this one I also needed to look at where we are in the last buffer. So this goes back to essentially the main part of this code is right here, where we're just using SciPy to create this square wave. But the little trick that I'm dealing with up here is best seen on this slide. So when we're creating this square wave, the frequency of the wave might not perfectly line up with where the buffer starts and ends. So we need to know if the last square wave, if we were in the middle of a wave at the top, bottom, or where we were in it. So you can kind of see there's a little bit of these little like notches where it's switching between buffers. But what I'm trying to do is make the sound more continuous by saying, okay, we're at the bottom of the square wave, start at the bottom and then go up. And then, or if we're at the top of a square wave, start at the top and go up and go down. So that helps to just to add a little bit of continuity and reduce the clipping. Yeah.
So what function is it? I'm trying to think through.
We're
identifying a frequency.
Yep. Yeah. So it's exactly how the tuner works, where we're computing a frequency to figure out the pitch, but we can instead figure out the frequency. We take that frequency and the amplitude that we're using and give it to this function called square, which is a SciPy function, and it'll just compute a square wave. Yep. And then I just tell it where on the wave I want it to start based on where the last wave ended. That makes sense. So that way that doesn't have the discontinuity jumps. But yeah, I'm just giving it the information it needs to create a function, and then it plots that. Yeah, and then this little bottom part, scale effect. So the square wave has just a ton more presence than the sound of a bass guitar. So I scaled it down 30%, so that way it's not so jarring. It's still a little bit, probably could go up a little bit, but if you don't scale it down, it really is like twice as loud as the normal bass. And I think it's just because of how long that the tops and bottom. Right, yeah.
Where?
Yeah. So it has a lot more presence. But yeah. Okay. So I think yeah, that was all I had. There's some additional resources I wanted to point out, which is I used a few images when I was explaining audio processing. Oh, I guess and it has a great overall description of how digital audio processing works. Yeah, I found it really helpful just for understanding exactly what was going on. And then I mentioned this earlier, but Spotify has a Python library called Pedalboard that has some really high quality manipulations you can do. When I put the slides together, it was only working off of audio files versus trying to do a live manipulation. But if you have some kind of professional effect and want Python to do it, that's a potential. I have the link to the GitHub, but I'll put that in the slides in the Discord. And then, yeah, I think I already, Xander already asked, but yeah, I'm using a Focusrite Scarlett Solo. And so what that does is it has a cord that's going from my bass to the instrument or to the Focusrite, and then it comes out into a USB that's going into the computer. And then I have on here, I can swap between a bunch of different input sources on my system, and same with output sources. So if anyone's interested in playing around with some of the other effects, yeah, you're welcome to download it and try out whatever you want. but yeah, that's all I had. I'm happy to take any questions. Yeah.
Any questions online or in the room?
What's your GUI?
It's built using PyQt6. So yeah, it's not. I made this recording thing a little bit bigger just because when I was testing it out, it seemed a little hard to see on Zoom at the same text size. But yeah, it has stuff about like you can manipulate the output volume. You can change whatever output driver you want. You can change the sample rate of the microphone. You can change the buffer size too. You can see there's all kinds of like if I change the buffer size to here, this like super long one, there's a huge latency between when I make a sound and when it comes up because of how much more data it has to capture. Yeah, it's probably tough for the people on Zoom to register what just happened, but um, yeah, there's a big latency between when I made a sound and when it came through. Yeah, good question. Yeah, anyone else have any questions? Oh, okay. I'll switch that. Oh, okay. Well, I'll switch that in 1 second. So I log into here. Yeah, thank you for that note. Okay.
How hard is it to get input from the audio device, like drivers and I don't know.
I did not have any issue. I just plugged it right in and then selected the source and it comes up. Yeah, I can swap between making my.
You can speak to it too, like sing to it and
Yeah, I could see what happens if I try to talk into it and put it out as a square effect. I don't know. All right. Test. Sorry about that, everyone. I could check. So,
that just identifies the frequency of your
yeah, and the amplitude and creates something. So I'm not sure if we startled other people in the building, but yeah. Yeah, I know one of the things I wanted to try to do but couldn't make it work was I wanted to make an octave switcher. So I really wanted to make it so, because theoretically all you need to do is double the frequency or half the frequency. And I could not get it to sound smooth with the buffers and getting it to like line up exactly where the next one should be, especially if you like don't just play the same note at the same volume. I couldn't quite get it to sound okay without a ton of clipping. So I had to bag that one. I had more luck doing it, something that's pre-recorded because you know exactly what you're dealing with and you can kind of break stuff up. But I couldn't get it to work in a real-time environment. But it was one of those things that seemed theoretically not that challenging, but there's some devils in the details.
How do you feel about playing something for us?
Playing some, I don't know.
We could jam out together.
I will say, despite my best efforts, there is still like a split-second latency between the sound, especially as it goes through everything, and so it gets really distracting trying to. Oh, sorry, still got in the microphone. It gets really tough to like play a long time without. Oh, I got this going way down. But it gets tough to like with the sound going like out at a different spot, slightly off. I don't know why that's acting so weird, but
so like all those like where you list out your audio inputs and your that all just comes from PyAudio.
Oh, that's a good question. Yeah, that is from PyAudio. Let me see if I can. They have like a really nice function that just you can just get all the input sources. Yeah, I'm all that's dedicated to or relegated to PyAudio. Same with the output sources, and then I just put it into a Qt. I think it's like a drop-down box or whatever they call it. I can't remember where I'm doing that, but oh yeah, add to each combo box. Yeah, I don't know if I want to. Can dive into where that is. Okay. Yeah, so PyAudio get input devices. Okay, yeah, I guess I was delegating it to a function that I was doing in here, but yeah, I had just looped through the device counts. I had to pull some info about it to figure out like the device name. So that's mostly what I'm doing here is just looping through each thing. I make sure that the maximum input channels is greater than 0. So sometimes you'll just look through something and it doesn't actually have any input channels. So I was skipping all those and then just grabbing the name. And then that's how I was building the input and output boxes. But yeah, this is the main same thing. PA is the PyAudio. I think I had to initialize it as a class object, which is why I have the self.pa. So I think you start it and then it'll go. Yeah, good question. Anyone else have any thoughts?
Program.
I did use some Copilot. Yeah. It does definitely, especially for I used it mostly for GUI stuff. I found that it's really nice for lining stuff up in GUIs. I mean, this isn't like the prettiest GUI, but
That's good.
it's super easy to get it to do a bunch of stuff to make things look all right. The actual like signal processing stuff, I had to do manual research, but I'm sure there's probably okay things. I did try having Copilot try to solve my clipping issue with the octaves, and it wasn't not quite there yet on the AI front. Yeah, but yeah, I do really enjoy using that for yeah, especially GUI stuff. Just so fun, so fast.
Andy Online said he loves seeing the link to physical and digital.
Oh,
Doing software with the physical world.
oh, cool. Oh, yeah.
Johnny's asking, can a link be posted in the chat for the GitHub repo?
Yes, but yeah, like someone pointed out, I need to make it not private, so it won't work at the moment, but I will fix it in a second. I just need to make sure. I think I'm gonna have to. There's the link to it. I just yeah, I'm gonna need to do a 2-factor authentication and all that to log into my GitHub. So I'll just wait till I'm not sharing my screen. Yeah. But yeah. Thanks for the interest in the. I guess I can also grab this. Post a link to this. Okay. Yeah, and then I'll put those links also in the Discord.
Any other questions, anyone?
Okay, thanks.